Hello again, everybody, and welcome to the webinar on solar desalination organized by the International Solar Energy Society. We will begin in a few minutes. Okay, I see that more attendees are joining our webinar. I'm just going to wait one more minute so that everybody can join. Great, okay. We're going to start the webinar now. Welcome everyone, and thank you for joining us today. It is the first webinar of 2015, and we are very pleased to have so many people participating in this ISIS webinar on solar desalination, current situation and trends. Before I go on to the agenda, some short housekeeping items. All the speakers' presentations are available in PDF format on the ISIS website. That's www.isis.org. Follow the links under the latest news announcement of this webinar to find the links to the presentations. You will also find a short presentation on our website under the title of this webinar with some technical information in case you are experiencing any problems during the webinar today. This webinar is being recorded. The recording will be available on our website in the next few days. During the webinar, you are welcome to ask questions at any time. To ask a question, please simply write your question in the questions window of the GoToWebinar software tool. Please specify who your question is directed to. I will then assign the question to the speaker. Some of the questions will be addressed after all the presentations in the Q&A session. We will try to answer as many questions as possible during the webinar, but I apologize if I do not get to answer your question because of time restrictions. I will collect all the questions with as many answers as possible and post them on the ISIS website with the recording in a few days. Good. Now I would like to show you a few things about the International Solar Energy Society. ISIS stands for the International Solar Energy Society, and for those of you who have never had any contact with us before, here's just a few bits of information for you. The International Solar Energy Society is a non-profit, UN-accredited membership NGO. We were founded in the USA 61 years ago, and today our headquarters are located in Freiburg in Germany. We work to achieve 100% renewable energy for all, used efficiently and wisely, by providing our members with a collective knowledge-based voice for solar energy research and development, sustainable global renewable energy industry, renewable energy issues worldwide, and energy education at all levels. Up-to-date critical information on technology and marketing, news, publications, networking, and business development opportunities, as well as training programs. Opportunities to network and work together on the energy transformation, be recognized for important contributions, and for the young ISIS members in particular, who are students or young professional members, opportunities to advance their careers in solar energy and related fields. We represent a diverse membership of academics, researchers, energy practitioners, consultants, students, businesses and advocates. ISIS also has sections in many countries around the world, working at the national level to advance renewable energy, and we partner with like-minded organizations to advance the renewable energy transformation. Thank you to everyone who has joined as an ISIS member already for supporting us in advancing the energy transformation. Okay, now I will move on and talk about the agenda for today. Our first speaker will be Baltasar Peñate Suarez. He holds a PhD in engineering from the University of Sevilla in Spain and is currently the head of the Water Department of Technology Institutes of Canary Islands in Spain, the ITC. Our next speaker will be Gonzalo Pierniviaje Izquierdo, who holds a degree in physics from the Ludwig Maximilian University, Germany, and is the director of the R&D division at the Technology Institute of Canary Islands in Spain, the ITC. The third speaker is Joachim Kosikowski and is the head of the team Decentralized Water Treatment at Fraunhofer Institute for Solar Energy Systems, ESA. Our final speaker is Diego Cesar Alacon Padilla, who has a degree in physics by the University of Granada and a PhD by the University of La Laguna. And since 1994, his research activity is linked to the Plataforma Solar de Almería in Spain, being the current responsible of the solar desalination R&D unit. After these presentations, we will have a questions and answers session, to which I invite you all to participate in. In order to type a question, please just write it into the questions window of the GoToWebinar software tool. Please state who your question is directed to, and I will assign it to that panelist. Good. Then without further ado, Baltasar, I can give you the floor. Baltasar?
Okay.
Yes, we can hear you.
Good afternoon. Okay. Good afternoon to the audience. Firstly, I would like to thank Solar Energy Society for giving us this opportunity to talk about the desalination with solar energy. Water availability in quality and quantity is one of the largest worldwide health matter of our time. 11% of the global population, almost 800 million people, are still without access. Many regions of the world are increasingly turning to desalination of brackish and seawater in their effort to supply fresh water when the increasing demand is not met without natural water resources. Desalination technology is fully mature and is present anywhere, especially in coastal areas with limited water resources. The trend to install desalination plants is intensified by climate change, which seems to be already affecting the water cycle, leading to long periods of drought. The desalination industry has responded well to increasing demand and is constantly evolving by reducing costs and reliably producing very high quality water. Most innovations are focused on reducing the energy demand of the desalination process. The specific energy consumption has been of especially interest, and this is the most variable in desalination plants' operation cost. it has a direct impact on the cost reduction of the desalted water. However, it will always require considerable amounts of energy. If conventional energy sources as used, they contribute to climate change, which in turn affects the water cycle and intensifies the original problem that desalination was intended to solve. For this reason, and in general, renewable energy sources must be used to meet at least part of its power requirements in the case of the high-scale capacities, or totally in the case of the low and medium scale. Most of the countries with water scarcity exhibit significant solar energy sources. Solar energy can be used directly in the case of the solar still, or indirectly by using solar collector connected to the desalination plant. The coupling of solar energy with desalination technologies is seen as having the potential to offer a sustainable route for increasing the supplies of desalinated water. Solar photovoltaic combined with reverse osmosis is a high-efficient reality from 10 years. Currently, thermal membrane distillation and concentrating solar power combined with multi-effect distillation plants are attracting all the interest. The integration of different solar power generation and desalination makes the solar power concept fully sustainable. This webinar is an introduction into the solar desalination field. It will show the current technology situation and trends. The three presentations chosen will present the state of the art, successful experience, and expected market drivers and challenges. Thank you for your participation and enjoy it.
Thank you, Baltazar. A few people have asked if the slides aren't working. They are working. We will have a look at the next speaker who has a presentation to show. The next speaker is Gonzalo, and he is showing his screen at the moment. Good, I can see that. Can you make it full screen mode, please? That's perfect. Thank you very much. Take it from here.
Okay. Hi to everyone. My name is Gonzalo, and I'm talking as Baltasar from the Canary Islands. So, short introduction about ourselves. We are a technology center. I missed putting the Canary Islands on the map. We are close to the West African coast, approximately 100 kilometers from the Moroccan coast, and we are specialized in renewable energies, water technologies, other fields like biotechnology, microalgae biotechnology, and in these fields we have been working for almost 20 years in developing solutions for electricity and water supply to remote areas. Because we are on islands, so we know the islands framework very well, but also our technology solutions can be applied to remote regions from to all over the world. So we have been very active in transferring technology that we have developed at our test site and developing site in Pozo Izquierdo in Gran Canaria Island to several countries, not only the countries that are our neighbors, like Morocco, Mauritania, Cape Verde, Senegal, or the ECOWAS countries, but also to Tunisia. So we would like to share with you some two outstanding projects we have been carrying out here, where desalination coupled with renewables has been implemented. One is HIERRO. It's the first 100% renewable energy island worldwide. So it's a not connected island to any other island or to the continent. And there we have last year commissioned a wind-pumped hydropower station where water has lots of uses, not also the use to make renewable energy stable, but also used for agriculture. And all the water comes from desalination plants. La Graciosa is a smaller project we are developing right now, and on an island of less than 1,000 people, where a small desalination plant powered by PV, by a PV microgrid, will be installed. This is just to show you how our activities are developed here on the islands. So we have also a training platform on that issue. It's shown on this slide. So we have already carried out 13 editions of this course, and you can click in the link later on and see what. Well, we will have another edition soon. So my speak will deal with particularly with the PV-RO case. RO means reverse osmosis and PV photovoltaics. So first a short introduction about the desalination, further to my colleague Baltasar, then a little bit about combinations between renewable energies and desalination, and particularly the PV-RO experience and our experience, because this is the technology at ITC where we know best. And then other initiatives that are taking place in the European scenario. So desalination is a growing field. We have seen lots of developments in the last, especially in the last 20 years. We in the Canary Islands were pioneers because in the beginning of the 60s we installed here the first desalination plants of Europe. And the geographical distribution is half of the desalination market is placed in the Middle East, and then you see almost 20% in America and almost 15% in Europe. The scales of these desalination plants vary, so there are plants from supplying very small populations, but there are very big plants. Actually, there are now plants being constructed with 1 million cubic meter per day normally, but we could say that 300,000 cubic meters per day production could be an average, 300, 200,000. And the global market approaches approximately 100 million, or will approach 100 million cubic meters per day in the next year. So we in the Canary Islands have less than 1 million, and we have one of the highest densities in the world. So there are different technologies. So the basic classification or the basic categories are those that are driven by thermal processes and those that are driven by membrane processes. So, and you see on this table all the energy sources, I mean the energy forms that power the different desalination technologies. So they can be either mechanical, thermal, electrical, or a combination of these three forms. So in the case of membrane processes, so then we don't have here an evaporation. So membrane processes is applying selective membranes, and then evaporation is using an evaporation condensation cycle. Here the goal is to, or the energy to be employed is to pump or to drive pumps. So this technology has advantages with respect to thermal processes, and the basic ones are that the membranes operate at ambient pressure, ambient temperature, not pressure. Pressure is a key factor here, but they operate at ambient temperature, and there is no change in phase. So the decision on what desalination to employ depends on many factors, and one very important factor is energy, because energy makes up almost 50% of all the costs of desalination process. So when there was cheap oil, with the exception of these last months, the thermal processes were the ones that were driving the market. And in the last year, in the last 10, 15 years, reverse osmosis is the process that is having all the market, or the majority of the market, because of the relative less specific energy consumption. So regarding the global market, there is $3 billion per year. So, and the average production cost of all systems is in the range of $0.75 per cubic meter. So there are the trend now is, or the three main desalination technologies that are now on the market are reverse osmosis, as said before, multi-effect distillation in very big plants, and multi-stage flash distillation. So one membrane process and two thermal processes. And so you see on this table all the features of the three processes. So regarding energy, we have, as I said before, energy consumption makes even up to 60% of the total water cost. So this is why we are here, sharing with you all this know-how here. So, in the case of seawater reverse osmosis, now it's possible to have a specific energy consumption that is kilowatt hours per cubic meter. So this is how it is measured here in this field, below 3. So 15 years ago we had 15. So now we have below 3, even sometimes below 2. So it's really a technology that is very efficient in energy. So the next slide, this slide shows all. It's a further classification of how to power the different processes, and we see electricity is needed to power RO, EDR, which means the electrodialysis, and vapor compression. VC means vapor compressions. Here, a compressor is powered via pumps, so driven by electricity. So the next slide goes deep into that and shows how the technologies that have been tested, and you see here the process, the potential renewable energy source, and the combinations that are that have been tested in the last 10, 15 years. So this is a really a rather new field. This desalination with renewables is approximately, I would say, 15 years old. I mean, was born before. It was born 100 years ago with a solar distillation unit. I think Joachim will speak about that, or Diego. But these more high-tech things have been developed in the last 10, 15 years. So here you see how the technology combinations that have been tested in this in the last years, and you see PDRO is let's say one of the best developed technologies. So in this slide you see. Please read it carefully, because we elaborated within the framework of a European project this table in 2012, and PV costs have dropped from that time. So if you see PVRO, we have to recalculate. We are actually now recalculating all this water generation costs, and maybe it would be 10 or to 20% lower than it's depicted in the table. And we can see it's a pre-commercial technology. PVRO is now a pre-commercial technology. So, but there are barriers for the commercial deployment, and you see the barriers there. So, what the biggest barrier, let's say, is the highest capex. You have both desalination capacity, but you have also renewable energy, and everyone, I believe everyone is aware that the capex is high, so this has to be dealt with different strategies, but we can say that these are technologies that are ready to be in the market right now. As I have already talked about that issue here, the barriers, but also the opportunities that these technologies show. So it's a matter of overcoming the barrier of highest capex. So we have been working in PVRO either standalone or grid connected. If you are operating PVRO in an off-grid, very remote area, so we are actually for the time being recommending coupling with batteries, so that you have a stable, because reverse osmosis has is sensible to fluctuations in energy. So we are advising to have battery in these systems. So here there's a list of all the experiences we have. We have installed several systems in not only in our test premises but also in Africa, and we have different designs. We have been working with brackish water, with seawater. We have managed to have specific energy consumptions below 3 kilowatt-hour per cubic meter. For seawater desalination, our experience is that we have a daily operation of between 8 to 10 hours, and these are the capex per installed capacity. So this would be the installation cost of such a system. So this is in Tunisia. It's a nice project in the middle of the desert, 200 kilometers away, 250 from Jerba Island, and there we installed a plant that's been now operating for more than 8 years successfully. So you have all the data there. Then later on we installed 4 brackish water systems in Morocco that have a raw water salinity of 2.5 to 8.7 grams per liter. That means grams per liter is the same as saying ppms, okay? And our systems have been in this range for supplying water to communities up to, let's say, 500 people. So this is the field where we see the most imminent markets. And finally, I would talk about another interesting combination for PV, and this is EDR, electrodialysis. I say it's nice because it's driven by direct current, so you can easily supply the plant with photovoltaic energy, avoiding the use of inverters. So, and the last slides, as I said in the beginning, there is let's say a motivation in the European arena regarding renewable energy desalination, and we are members of an action group that we are activating together with the partners that are following me right now. So there is a increasing interest in Europe, and I hope that this is you see Guillermo Zaragoza, the contact. If you are interested, please send me an email, and okay, and thank you very much for your attention. I think I have kept the time.
Yes.
And there you have our email and our contacts. So thank you for listening to us.
Okay, very good. Thank you very much, Baltazar and Gonzalo, for your excellent presentation and your information from the Canary Islands. We have a few questions that have come in. Maybe you can answer them quickly for us. Is that okay? The first question is, Gonzalo, are you still there? Can you hear me? Good. The first question we have is, what is IDA? So I think this
is the International Desalination Association. It's a big international association that has all desalination professionals in.
Okay, great, good. That answers the question. One more question as well is, how did you know the water quality of the project sites that were chosen for the example plants?
Yeah, this is very important. So we have to analyze, we have to get samples. Previous to any design, this is the most important factor, to analyze the quality of the raw water. So you have to make an analysis of the water.
Very good.
The main salts and also the salinity itself.
He also asks, were there well logs that you could go off of? Well logs.
Well logs.
Talking about the water quality.
Yeah, there are two main sources in these technologies. We have seawater. The source is the sea, but it's not so easy to get the intake from the sea. So we in most of the installations we drill beach wells to extract the seawater, and for brackish water desalination plants we take existing wells. Okay, so existing wells that all these areas where we have been working on, they have the problem that the water gets salty. So this is why we go there. So we measure the salinity of the water of existing wells, and we take the existing well as the intake to the desalination.
Okay, the person has written back now that he meant geophysical well logs and that he has his information. Thank you very much. Okay, there's many more questions that have come in, but we'll answer them after all the presentations. Okay, thank you very much, Gonzalo and Baltazar. I will now change the presenter to be Joachim Kosiewski. So Joachim, you now have the floor. Could you please unmute your microphone? Yes. Good. At the moment we are seeing your, yes, exactly, now we see your presentation.
So, good afternoon, everyone from Freiburg. My name is Joachim Kosiewski. I'm working with Fraunhofer Institute for Solar Energy Systems. And we have a group of about 10 employees here in the Institute working on the topic of solar desalination. And in the next 15 to 20 minutes, I want to introduce a technology which is not that much known because it's not applied for large-scale desalination. The name is membrane distillation, so it joins membrane technology with a thermal desalination technology. I will introduce the transport phenomena, give you an idea about the basic membrane distillation configurations, and show you some slides of our pilot systems and have a short conclusion. So the core of the membrane distillation process is a hydrophobic microporous membrane. The membrane material is typically polytetrafluoroethylene or polypropylene, and the pores are in the order of 0.1 to 0.4 micrometers, so they are relatively big, but due to the hydrophobic nature of the material and the polarity of the water, liquid water cannot penetrate these pores. But if you add a water temperature difference between hot saltwater side on the one side of this membrane and a condenser side where you have pure water, then with this temperature difference, driving force is established, and this driving force makes water vapor molecules passing from the hot feed side to the cold pure water side. You can calculate this from the equation which is shown here. It on the one hand there is a membrane constant which mainly characterize the properties of the membrane itself. So there's a Knudsen diffusion and molecular diffusion coefficients which describe the properties of the pores and the material and the non-dissolved gases in the pores. And you have the driving force, which is established by the temperature difference, as I said before. And you can see in this graph here how this driving force, respectively the pressure difference, can be calculated from the Clausius-Chaperon equation. So the blue line, for instance, is a water vapor pressure with respect to temperature. So at 100 degrees centigrade, there is a boiling temperature and 1 bar pressure is achieved. So if we assume that we have a temperature difference of 10 Kelvin between the hot feed side, which is probably 90 degrees centigrade, and the cold permeate side, which is probably 80 degrees centigrade, then you see that according to this temperature difference, water vapor pressure partial difference is established of about 0.22 bars. And you also see from this graph that if you drop down the average temperature, let's say to 50, 60, then of course also the driving force getting lower. At the same time, you see also from this graph that this technology is affected, but not that much as others, by salinity. So the red line that you see here is the water vapor pressure of saline water, of a salinity of 150 grams salt per liter of water, which is 6 times more than seawater, but to make it visible, I chose that. So you see accordingly that for higher salinities, with respect to this graph, the driving force is getting lower, but you also see that this technology can be pretty good be applied to this high salinities, which is not possible for other technologies as reverse osmosis, for instance, which is pretty much limited by osmotic pressures. So according to the heat transfer, according to the mass transfer through the membrane, we also find significant heat transfer. On the one hand, we have the heat, the latent heat of evaporation, which is transferred with the vapor from the hot membrane interface to the condenser side. So we have latent heat, and on the other hand, we have also heat conduction. The membrane have a diameter of about, or thickness of about 200 to 300 microns. So you can imagine if there are two streams, that there's also a lot of heat conduction through the membrane, and this heat conduction can be considered as parasitic because it does not contribute to mass transfer. So we find different basic membrane distillation configurations, which take also this into account, what I said before. The easiest combination or easiest design configuration is a direct contact membrane distillation, as I showed you before. There's a hot saltwater stream on the one side of the membrane and a cold pure water stream on the other side, and water vapor passes through the membrane is condensed on the permeate side. To take into account the parasitic heat losses, the air gap, which is number C here, the air gap configuration has a gap behind the membrane and a condenser sheet. So heat conduction is avoided by the gap, and the water vapor which penetrates through the membrane is condensed on the back side, so on the condenser sheet here, and the heat is transferred to the coolant. The disadvantage is that the air gap is another resistant for the water vapor, so the mass transfer is reduced by the air gap, but if the non-dissolved gases or the air is derated by applying vacuum, then also mass transfer is pretty well. So, and another configuration that joins both A and C is that what we call permeate gap distillation, where we have also a condenser sheet or impermeable film in the module that separates the permeate channel from the coolant channel. And so we can reduce the heat conduction a little bit. And on the other hand, we don't have the additional gap or the additional barrier of air that reduces mass flow. So another advantage is that we can directly use seawater as a coolant here in the coolant channel. I will not talk about vacuum membrane. That's another story. So one of the most important properties of a sophisticated thermal desalination system today is a heat recovery device. So in membrane distillation, you can achieve this when you have very long channels. So you see on this slide a membrane distillation module in permeate gap configuration. So the evaporator channel on the left-hand side, then the permeate gap with where the distillate or the permeate is collected, and the condenser side, condenser channel. And so assume that water, seawater enters the condenser channel at about 20 degrees centigrade on the bottom here at number 1. Then it's preheated in this channel. The channel length may be 7 to 10 meters. We assume that it's preheated because the latent heat as well as some heat conduction heats it up to about 72 degrees centigrade. Then it's introduced into a heat exchanger or a solar thermal collector, and the temperature has to be increased only by about 8 Kelvin to achieve the top brine temperature for the evaporator. And then we see during when the feed flows through the evaporator channel, temperature drops down again, and along the whole channel, the temperature difference of about 8 Kelvin is established, and this is a driving force making water vapor passing from the evaporator to the condenser channel. You can also see, of course, as I mentioned earlier, at high temperatures, you see that on the left-hand side of the graph, at high temperatures, the flux in each the flux is much higher than in the low temperature zones of the module. But with respect to heat transfer, it's quite important to have huge surfaces, and that's also the trade-offs that you have to be aware of if you want to optimize the membrane distillation process. If you are talking with people from membrane technology, then they always look on the flux, so how much a kilogram permeate per square meter of membrane is produced. On the other hand, if you are talking with people from thermal distillation, then they are very much focused on the DUR, on the gain recovery ratio, and which indicates the efficiency of the heat recovery. But it's also obvious that you cannot optimize both at the same time. So you have to go for large surfaces to optimize the heat recovery, or if you want to optimize the flux, then you need very high delta T's, high driving forces, and small or low small surface areas, so to increase the flux. We made simulation calculations for all different membrane distillation configurations, and this simulated points here show pretty good that you always have to make a trade-off between heat recovery or and flux. So you can achieve pretty high flux values with membrane distillation, which are far above reverse osmosis. We can achieve 50-60 kilogram per square meter. But on the other hand, then the heat recovery is pretty poor. On the other hand, we can achieve very high DUR values of up to 9. But on the other hand, flux values are pretty low then. So different module configurations exist. In Fraunhofer, we mainly design spiral wound configurations with about 10 to 14 square meter membrane area, but we also have plate and frame modules, so both configurations are possible. In the institute we have a device to produce the spiral wound modules. You see a winding machine on the left hand side. There are all the different materials, membranes, spacers, condenser sheets, which are winded together here. And we also have small plate and frame modules together with our spin-off company, Solar Spring. So now I want to show you some pictures of the pilot plants that we installed so far. We installed in the beginning of 2000 with membrane distillation, and we follow two different basic designs. On the left-hand side, there's that what we call compact system. in this design. We preheat the water, the feed water or the seawater in the module, as I showed you before, and then the preheated feed water is introduced directly into a solar thermal collector. The thermal collector must have seawater resistant tubes, but the advantage is that we don't need an additional heat exchanger in this place here. And then we increase the temperature with the solar thermal collector by 8 to 10 Kelvin and introduce a hot feed into the membrane module. This system runs pretty good, also with alternating energy supply, so if much heat is available then we run a high volume flow, and if low, the sun is down, then we run or the sun is up, then we run a high volume flow in order to adapt the inlet temperature of the module. So for nighttime operation and for larger plants, we recommend a two-loop system. In this configuration, we separate the solar loop completely from the desalination loop and we transfer the heat via heat exchanger. The advantage is that we do not need seawater resistant collectors in this case, and that we can store the energy and that we can run the system also in the evening or also during night time. And we can operate the system also always on the optimal performance level of the membrane modules. So this is again a picture. This on the left-hand side, that's the very first compact system that we designed together with ITC in Gran Canaria with my colleagues, and I hope it's still standing there, and I don't know if it's still running. On the right-hand side, there's a sketch that I already introduced to you. So this is another small unit that we designed for another place. So the capacity is quite low. It's only 150 liters per day from 6.8 square meter collector area. But it's much more, of course, than in a simple solar still, which has no heat recovery. So the more sophisticated system is, as I said, the two-loop system. In this case, it was a design for installation in the north of Namibia, in the middle of nowhere, so transportation issues were concerned. So we designed the system such that it was mounted completely into a 20 feet container. So what you see in the back side is only the heat storage, a 12 cubic meter heat storage, and in the front there we have 12 membrane distillation modules which can operate with the heat from the storage and the collector field respectively. So what you see on the right hand side is a back side of the container, and we have a cooling tower there. Maybe you remember that the brine that leaves the membrane distillation module has always a higher temperature than the condenser inlet, and so if we want to recirculate the water and reuse the brine as a coolant, then we have to cool it down, and therefore we use this dry cooling tower here. So that's the internal view from the container. You can see it's a prototype, and on the right hand side there's also the collector area, which has a size of about 220 square meter. Another system that was installed in the frame of the Medeiros project, EU FP7 project, was installed in the south of Sicily on a small island, and it was and is still operated with waste heat from a large diesel engine, and the system consists of 12 membrane modules and is supposed to produce about 5 cubic meter of fresh water per day. And what you can see pretty well from this investigations here is how the system reacts to salinity. So we recirculated the feed water in the system, and so we increased step by step the salinity. And what you can see is that, for instance, the orange curve is a salinity of 45 gram per kilogram, and if we increase the salinity to 57, then we see already that there is a decrease in flux or in productivity, and if we increase the salinity further to 100 gram per kilogram, which is quite high for other technologies, then we see that there is a decrease of about 30%, but the technology still works and pure water is still produced. So, and this is one of the big advantages of membrane distillation, that you can apply it also for very high salinities. And last but not least, we also installed a containerized system together with our colleagues from ITC and other partners in the Canary Islands. This is also a 5 cubic meter system produced with a solar field about 3.5 cubic meter per day. The solar area that we installed had a size of about 180 square meters. So I come to my conclusions. So the advantages of membrane distillation. We have a good compromise between efficiency and complexity. Specific heat consumption can be achieved below 60 kilowatt-hour per cubic meter. It's not today, but that's possible in the future. The feed temperatures which can be used, it depends a little bit on the configuration of the membrane distillation system. But it can be between 50 and 90 degrees centigrade, so also low-grade waste heat can be used, or heat from solar thermal collectors, or also heat from CSP power plants. The sensitivity against fouling and scaling is relatively low compared to other technologies. One big advantage with respect to solar is that the transient operation is possible as in temperature as well as in feed flow. We can vary it, and the technology, the membrane distillation follows. As already said, high salinities can be treated depending on system configuration, and it can also be used to concentrate the brine close to saturation, so that it could be also used as a pretreatment step for zero liquid discharge. Basically, the product water is of a very high purity because it's distillate, and I think that there is a huge potential for cost reduction because all parts in the module are made from polymers. So finally, at the end, we can use polypropylene for everything. Polypropylene is quite cheap and can also be recycled. So finally, there should follow now the disadvantages, but they don't appear though. So there are.
Yes, we see them.
Okay, so it has to be said that the laws of thermodynamics are also valid for membrane distillation, so the energy demand is still high compared to other technologies as reverse osmosis, if we are talking about seawater or brackish water desalination. So the electrical energy demand to drive the circulation pump is about 1 to 2 kilowatt-hour per cubic meter, and the thermal energy demand is still in the range of, let's say, in the future, 50 to 100 kilowatt-hour per cubic meter. Today there are no membranes available which are really optimized for membrane distillation, so there's also a big effort to be done. The long lifetime is still not proven, even if we have some units running for a couple of years now, but compared to other technologies which are really major as reverse osmosis or MED, membrane distillation is still a very young technology. And finally, no large-scale industrial systems are in the market today, so scaling up the technology is still a big task which must be done to make it also applicable in the future as a competitive technology. So that's it. I thank you for your attention. I hope it was not too scientific. Thank you, and maybe there are some questions later on.
Good. Thank you very much, Joachim, for that excellent presentation and information. We have many questions that have come in. Maybe you can answer one question now, because I find it very interesting, and I think our audience does too. And the question is, what kind of post-treatment would you do to the desalinate obtained from MD technology in order to make it suitable for human consumption?
Yeah, that's a very good question. Because everyone is really afraid to drink ultra pure water, but it's not that bad to drink it because most of the minerals you take by your food. But usually we remineralize it, as it's also done in large-scale multi-effect or MSF plants, because they also produce pure water and then it's remineralized.
Okay, good. Thank you very much. Now I will make Diego Alarcón the presenter. Thank you again, Joachim.
Yeah, welcome. Thank you for the invitation.
Okay, Diego, you have the floor. Please unmute your microphone.
Okay, good morning. Do you see my presentation?
Yes, yes.
Okay. Good afternoon to everybody. Thank you very much to ISES to give me the opportunity to be one of the presenters in today's webinar, and also thank you to the audience to be still here and to see my presentation. Today I am going to talk about the topic of cogeneration schemes for simultaneous production of electricity and desalinated water. And I want to say in advance that I am going to focus my presentation in what we consider large production of electricity and water. Let's say that we are talking here to produce electricity in the order of several megawatts and water in the order of more than 5,000, 10,000 cubic meters per day. We are not going to talk about the ideas of small isolated systems. So what is the motivation of this research line that is one of the activities that we have here at the Plataforma Solar de Almería within our solar desalination unit? It is a well-known fact that the increase of the world population, the industrial agricultural production, and together with the contamination of the city water resources is generating an increasing demand of energy and fresh water at global level. If you observe that two typical maps that we have, one about the solar radiation and the other one about the existing freshwater resources in the world, everybody knows that we have usually the usual coincidence of high water scarcity problems with very high solar irradiation levels. So this coincidence is not only geographical but also seasonal. So it seems for that reason that the integration of solar thermal power plants and desalination plants in one unique plant could be a sustainable solution for trying to alleviate the problem of energy and water. Talking about solar concentrating technologies to produce electricity, I don't know if all the audience is aware of it, the different technologies. We have solar central receivers, we have parabolic trap solar collectors, we have linear Fresnel collectors, and we have parabolic dishes. In all of them, we obtain very high temperatures in order to drive an electricity production cycle. So here in this picture you have the typical scheme of a solar thermal parabolic traps plant for production of electricity. And the idea is that you see, like in a typical thermal fossil fuel plant, from all the thermal energy that we are able to supply from the solar system, let's say the 100%, the typical ranking efficiency that we have in this kind of plants, in a typical commercial plant, is around 40%. And in the case of that we have temperatures in the condenser in the order of 40 degrees, almost 60% of the energy at this temperature, 40 degrees, is released to the ambient. So that can lead us to think that we should think about how we cannot take advantage of all this thermal energy that is released to the ambient. Also, a topic that makes us to think about the good opportunity for CSP plus D plants is that the issue of the water consumption in CSP plants. In a conventional solar, in a typical solar thermal power plant, the specific requirements for cooling water are higher than in a typical solar power plant. For example, you see in a typical solar power plant, the temperature entropy diagram, you see, when you work, for example, at 530 degrees Celsius, you had this typical cycle. But, for example, in a parabolic flat solar plant, the top temperature today is typically 400 degrees Celsius. So you have this cycle here. If you compare, if you see it, that means that the cooling requirements are more or less the same, but obviously, in the case of the fossil fuel plant, the electricity produced is more. So that means that we are going to consume more cubic meters in the case of a water-cooled plant per megawatt hour of electricity produced. In particular, for example, for a typical plant of 50 megawatt electrical, the typical consumption of water is around 6 cubic meters per megawatt hour, which means around 1,600 cubic meters per day. Obviously, the option to have a wet cooling system in a solar power plant could be dry cooling, but dry cooling implies that you are going to have a 3% higher investment in the cost of the plant, and also because dry cooling, the temperature that you are going to have in the condenser is higher than in the case of the wet cooling, you are going to lose around 3% lower overall efficiency of the plant. So all those things makes to us think that the simultaneous production of electricity and desalinated water can be an attractive solution for all the reasons that you have here, that we can identify technological synergies in order to reduce the combined cost of both electricity and the water produced. Also, when we have a local production of water and electricity, we can adapt easily to the specific demands of the location where we are. But apart from all those benefits, we should think also about the drawbacks. And what are the drawbacks? Obviously, the CSP plus D plants need to be located near the sea, where you know that usually a solar thermal concentrating plant requires a large surface of area in order to install the solar collectors. And this is not easy always in the coast, where you know that the land is not easily available and can be a big problem. Also, you know that the direct normal irradiance values that we have near the coast are not so high that we have inland. And that means that we are going to require a larger surface area of collectors. And also other technological aspects, for example, the resistance of the solar, because the solar collectors at the end are metal, are glass, and obviously you are going to have a very stressing ambient. For example, saline ambient is not very good for solar devices. So, looking at what are the best desalination technologies that can be coupled to a solar thermal power plant, as it has been explained by our colleagues in the previous presentations, there are several desalination technologies that has been proposed along the year, but only a few ones are today implemented at industrial level. We have multi-stage flash evaporation, we have multi-effect distillation, we have reverse osmosis, we have electrolysis, we have mechanical vapor compression. If you see here the most important, the ones that has been more implemented at industrial level, we have these four. And if we focus only in the thermal technologies that we can take advantage of the thermal energy that we release in a solar thermal power plant, we have two options. We have multi-stage flash evaporation and we have multi-effect distillation. In low temperature mode or in thermal compression. We will see later the main difference. If we compare the two processes, multi-stage flash evaporation has a large consumption of energy compared with multi-effect distillation, either in thermal and also in electricity, in power. So this is the reason why most of the analyses that are made and at the academic level are using the technology, are proposing the technology of multi-effect distillation. But I have to say that in principle the CSP plus D concept is open to any thermal distillation process that can have let's say a high thermal performance. For example, Joachim has been explaining membrane distillation. So in principle, if we have a development of membrane distillation in the next years, we can reach values of GOR or thermal performance about 10, 15, let's say 15, low electricity consumption. It can be also a solution to be coupled to a solar thermal power plant. For all the people, all the audience that doesn't know anything about desalination, very quickly, this is the typical scheme of a low temperature multi-effect distillation process. The idea is that we have a series of vessels where we have simultaneous processes of evaporation of the seawater and condensation of the vapor produced that is free of salt, and that condensate vapor is or distillate production. The typical top temperature that we need in a low temperature multi-effect distillation plant is vapor at 70 degrees Celsius, and we supply it uniquely in the top temperature first stage of the multi-effect, and the evaporation process in the rest of the stages is driven by the condensation of the steam that is produced in the previous stage. This is the idea. The larger the number of stages, the larger is the thermal performance of the plant. Obviously, to have the evaporation processes in all these temperatures that are below ambient, we need vacuum inside the unit. We can go from 70 degrees, as I said to you, is the top temperature in the first effect in order to avoid a scaling problem, up to a lower temperature that is mainly fixed by what is your low temperature at the final condenser, that usually is fixed by the temperature of the seawater. Typically, the top number of effects that we can find in multi-effect distillation is between 14, 16 at maximum. As I said to you, the higher the number of effects, the higher the thermal performance of the plant. And one variation of this process is multi-effect distillation with thermocompression. The idea is to have a multi-effect distillation plant like the one we have described, and we incorporate a thermal compressor where we have intermediate or at the end extraction, partial extraction of the vapor that is produced in the multi-effect, and use a high pressure steam. We mix it in a steam injector. At the outlet of the steam injector, we have the conditions required by the first effect that are steam at 70 degrees Celsius to drive the multi-effect distillation process. So the advantages of thermocompression is that we increase the thermal performance of the plant, but obviously at the cost of using, in this case, the energy, thermal energy that drives the process is not low temperature steam at 70 degrees, is the high pressure or medium pressure steam that we introduce into the thermal compressor. So, what are the typical configurations that we can propose for a CSP plus D plant? Okay, this is the more simple. The idea is that we remove completely the condenser of the solar power plant, and instead of have that condenser, we install a low temperature multi-effect distillation plant. So what are the consequences of this? The typical consequence of this is that we are going to have a higher temperature here at the outlet of the low pressure turbine, because, as I said before, the typical top temperature that we need here is 70 degrees Celsius. So in a typical standalone solar thermal power plant, we can have, in the case of water cooling, evaporative water cooling, we have a temperature around 40-45 degrees Celsius. And in the case of dry cooling, the typical temperature that we can have it could be 50 degrees Celsius in winter, or it could be around 60 degrees Celsius in summer, because the temperature is related with ambient temperature. So that means that introducing the low temperature MED plant is not free for the solar power plant. We are penalizing a little bit more the electricity production of the plant. And this is something that we should take into account, because sometimes we saw some studies that they say that the energy here is completely free, which is not true, because this energy that goes here has a cost, the cost of the kilowatt hour that we are not producing in order as a consequence of increasing the temperature in the first effect. What is obviously here we have the consequence that we have a fixed ratio between the electricity produced and the water produced, because the thermal energy that we have here is fixed by the power plant, by the size of the power plant. An option to that we call the configuration 2 is to use multi-effect distillation with thermocompression. You have here the plant with the steam injector, and in this case we have the low pressure steam comes from the multi-effect distillation plant, and we have to drive the steam injector with medium or high pressure steam coming from the multi-effect distillation plant. So what are the consequences or the advantages of that? In this case, we don't remove the condenser like in the previous case. So in principle, we can shut down the MED plant, and we can still producing electricity. It's not the case in the previous configuration that if you have a problem with the MED plant, you have to shut down the power plant. The disadvantage that instead of using low pressure steam, now we are using high pressure steam. So we have a high, let's say, a higher penalization in the power production process. As I said before, here in this case we can have a desalination capacity that doesn't follow the power production capacity. So we have the ratio that we really need for the specific location, and that's all that we can comment about this. The third configuration, obviously, is a special one that we have tested. We have studied here at the Plataforma Solar. It's low temperature multi-effect distillation. We have also a steam injector, but in this case, instead of recovering low pressure steam coming from the multi-effect distillation plant, the idea is to try to recover the low pressure steam that we have at the outlet of the turbine. Okay, and we mix this low pressure steam at, let's say, 40-50 degrees with medium pressure, high pressure steam coming from the other parts of the power block. And we run a completely conventional low temperature multi-effect distillation plant. In this case, we still conserve the final condenser, so we can make independent the power production process from the fresh water production process. Okay. In this case, we are taking advantage of, we don't need to condense, the size of the condenser could be a little bit smaller. And we have all the advantages that we have mentioned in the previous configuration. And obviously, the fourth configuration is the one that I don't like to say that this is not cogeneration. This is typically, okay, the idea that I have my power plant, okay, that I can put in whatever the location I desire, the most appropriate, and my idea is to produce all the electricity that I can, and at the end I use part of this electricity to drive a reverse osmosis plant. In this case, there is no penalties in the efficiency of the power cycle because we are still working at the same condition that when we have the standalone power plant. The production of water and electricity is obviously completely separated, okay, and the refrigeration needs are exactly the same that we have in a power plant because there is no exhaust vapor to condense. In this configuration, obviously, we are not taking advantage of any of the thermal energy that we are releasing here at to the environment. So I know that most of the audience are expecting from that kind of presentation to say, okay, but what is the cost of the water with that configuration? And what I have put this, I don't like to give a unique answer to that because the answer to that question depends strongly of the location and the boundary condition that you have in the location where you are going to install your CSP plus D facility. So the idea is that always when we are going to analyze a CSP plus D configuration and say, okay, what is the best option? To have a real cogeneration scheme with a CSP plant and a solar thermal desalination system, or it's better to have the separate production, first electricity and then reverse osmosis plant. So we have to make a deep study of that. First, obviously, if we are in a location where, for example, due to the salinity, due to the temperature of the water, due to contamination problems, that you are not able to install a reverse osmosis plant, obviously the best option is a thermal desalination plant coupled to a solar thermal power plant. Okay. If you don't have problem for that kind of problem for reverse osmosis, obviously the best option, the choice of the best option is going to depend what is the cooling method available for you for your power plant, because obviously the less the penalization in the power production due to the introduction of the solar thermal desalination plant, then the configurations with thermal desalination and power plant are better than in the case of reverse osmosis. That is, for example, if you have in the Mediterranean Sea, in the case of the Mediterranean Sea, you have an evaporative cooling method with 40 degrees only, I can say to you that the reverse osmosis is going always to be the best option. Okay, but for example, if you go to the Middle East, to a place where you don't have the possibility to have evaporative cooling methods, so you have dry cooling, you have a temperature of 60 degrees, and you have a high salinity of water, so you make that the reverse osmosis is working a little bit far from the most optimum condition that we can find today with value of 3 kWh per cubic meter of production. In that cases, the cogeneration scheme have an opportunity against reverse osmosis. Okay, for example, I have not put any slide in this presentation because it's a study that is going to be published in the next weeks or maybe in 1 month in the Desalination Journal. We have made a case study for one location in Almeria in Spain and also another one in the Middle East. And I have to say to you that the typical cost of this kind of scheme could be around €1 per cubic meter of water produced, and with our electricity cost of around 18 cents per kilowatt hour. That's the value that we are currently obtaining with this kind of cogeneration plants working with solar thermal. And that's all. Thank you very much for your attention. I will answer your questions if I can.
Thank you very much, Diego, for your excellent presentation and the information about the case study that you gave at the end. That's very interesting. We have many questions that have come in for you. I will read 1 or 2 out for you now. One question is, why is DNI lower close to the sea or the coast?
Well, this is typically because you have some DNI is direct normal irradiance. Is the rays that you get directly from the solar disk. And this direct normal irradiation is the only one that solar concentrating technologies can take advantage of. Okay? So typically, if you live near the coast, you can see that always you have some, I don't know, let me wait one moment. You have atmospheric effects like the presence of clouds, so you have no clear sky. So you have a lot of diffuse radiation. But solar concentrated technology cannot take advantage of it. And that is the reason why DNR values are always lower near the coast, due to the effects of atmospheric effects that you have near the coast.
Okay, thank you very much.
High humidity.
Here we have another question that's come in. Is the dry cooling condenser widely used? And talking about high cost of investment, can the gain in water consumption compensate the losses in investment?
Yeah, regarding the answer, there are some, for example, there is one plant, for example, in Abu Dhabi that uses that kind of dry cooling, because there is no water available to refrigerate the power cycle. So it depends. If you have, obviously, for example, solar power plants that are here in Spain, the commercial solar power plant, they have water available and they use water cooling because it's very nice to have 40 degrees at the condenser and produce as much electricity as they can. Okay, but I didn't understand the second point. Is obviously it depends of when if the increase in the investment cost of dry cooling compensates the cost of the water required.
Yes. So about the high.
You have to make a specific study. Obviously, people, if they have water available at low cost, they are going to use water. Most in the scenario, for example, here in Spain, that you have a premium for the electricity produced. So the people want to produce as much as electricity as possible. This is something I forgot to explain in my presentation, that when the people doesn't like very much the coupling of a desalination plant to a power production plant, because most of the time you have a scheme, public scheme, that they give a premium to you for the electricity produced. So when you come with a desalination plant and you say, okay, I am going to couple the desalination plant and you are going to produce less electricity. Obviously, the electricity producers say, I don't want that because I want to receive all the premiums for the kilowatt hour. So because always there is a premium for the electricity produced, but there is no a premium for the desalinated water produced with solar energy. So this is something that we should take into account, that we require it in order to promote the installation of CSP+D plants. We need to promote to maybe a premium for the electricity, but at the same time a premium for the water produced by the solar cogeneration plant.
Okay, thank you very much, Diego. I'll move on to our questions and answers session. One moment, please, till I change the screen. Okay, so thank you very much to all the panelists for your presentations. There have been many questions coming in, and I've now unmuted all the microphones because I'm going to ask you some of the questions. Okay, I'll start with Joachim. One question came in.
Okay.
How are the evaporator side filtered and maintained, and what is the lifespan of the MD unit?
So usually we have cartridge filters in front as a pre-treatment, and also acid dosing in case of high risk for scaling. So it depends pretty much on the raw water conditions. So the unit in the Canary Islands, which is running with water from a beach well, that's only filtered with a cartridge filter, and the system is running for a couple of years now. So with respect to the lifetime, I tried not to make any general statements today because the technology is not was not tested for so long, but we've experienced for, let's say, 3 years now with membranes which work well. We assume that in the near future we will arrive lifetime of about 5 years with smart membrane if our water conditions are allowed that.
Good. Okay, thank you very much. I have a question directed at all the speakers, so whoever would like to answer, please just freely answer. Who primarily funds these renewable energy desalination projects in places like Tunisia, Morocco, Cape Verde, Senegal, etc.?
So maybe I can start.
For us, maybe Joachim, yes, please.
No, please go ahead. Please go ahead.
So our experience, we have carried out all these projects in the frame of cooperation, international cooperation activities. On one hand, funded by the governments, I mean by the governments of the developed countries, through their cooperation agencies like ISEED in Spain, and also with the support of the European Union. So this was the fact until now. Now we think that with the drops in costs, all projects can be, let's say, or are ready for being commercially mature in the next years. So, so we will have to find some financial strategies to make them affordable for these local communities which are actually poor. But over the lifespan of the project are attractive from the financial point of view.
Okay, thank you very much. I'll go on to our next question, or does somebody have something to add? Okay, our next question is, how does RO and MD compare?
Yes, RO and electrodialysis case are both.
No, MD. I think it's a question for Joachim.
I
think this is for you, Joachim.
Yeah.
May I answer this question?
It's a question to Joachim.
Yeah.
How does RO and MD compare?
Mm-hmm. So the first thing, from technical point of view, as I showed, MD is driven mainly by heat, by temperature difference, and reverse osmosis is driven by pressure, with a pressure pump. So it's basically completely different. So with respect to maturity level, reverse osmosis was developed during the last, 30, 40 years. So it's now applied in very large plants, up to 500,000 cubic meters. Membrane distillation is still a very only on very small scale. With respect to
what about the costs? He's asking.
Yeah. With respect to costs, it's quite difficult to say today because the maturity levels are completely different. So membrane distillation is not produced in large scale today, so we don't have the numbers. But what I can say is that the costs for water from membrane distillation mainly depend on the cost of energy, of the availability of heat. So whenever heat is available for free, there's waste heat, then membrane distillation is comparative. But if we have to pay for heat, for fuel, or also for solar thermal collectors, and it will be quite difficult. So I see that that membrane distillation has more good opportunities on the downstream of reverse osmosis, for instance, to treat brine from reverse osmosis, because, as I showed before, it can be applied also for high salinity water. Or wherever heat is available for free from geothermal sources, for instance.
Okay, thank you. There are so many more questions that have just come in, but we don't have enough time for all of them. I have a question here for Diego. What is the maximum capacity of water and power for CSP desalination cogen already installed worldwide?
No. Precisely that. I haven't put you any picture,
okay.
Precisely because there is no real implementation of solar CSP plus B plants. It is clear that the concept of cogeneration, conventional cogeneration, is a concept that is well known, that is widely used in the Middle East, where you have always the usual configuration is that you have a conventional power plant next to a thermal desalination plant, either MSF, either a multi-effect distillation. But if you are looking for real implementation, there are only small pilot plants. That, for example, now there is for example, the one that Joaquin has presented. Well, but I think it's not solar. Is using waste heat. But there is now one pilot plant that is being implemented in Cyprus by the Cyprus Institute, that is going to be a solar tower for production of electricity with a turbine, and they are going to use the low pressure steam coming exhausted from the turbine to run a 4-stage multi-effect distillation plant. I think it's in principle the operation is expected for the beginning of this year, maybe in summer of this year. But there is no real implementation of that kind of plants. It's only research at level.
Okay, thank you very much. There are still so many questions coming in, but unfortunately we have no more time left. What I will do is I will collect all these really interesting questions and send them to the panelists, and we'll try to get answers to you as soon as possible. We will post the questions and the answers in an Excel file on our website, which I've sent the link to, and the recording of the webinar will also be available on our website. Then, thank you very much to all our panelists for being speakers today in this ISIS webinar. You have given up your time voluntarily to share your expert knowledge. We very much appreciate it. Thank you. And thank you to our audience for joining us today. We are looking forward to welcoming you to another ISIS event. Our next webinar is in February and will be on solar data resource applications. And I wish you all a nice day. Thank you once again. Goodbye.
Thank you. Goodbye.
See you.
See you.